There we go. So I forgot to release this assignment. It's about relations. So I'm releasing it today. I'll talk about it in 3 minutes. And I really like, some people are starting to use the questions in the channel. So that's good. I mean, that's what it's intended for. Is for you guys to come up with questions, and then you can either answer the questions yourself, or you can just leave it to me or somebody else to answer those questions. That's pretty much the intention of the questions channel. So if I sound a little tired today, that's because I really am tired. Have not been exercising for a while, and today I had to go out to the yard and basically level a, I would say, 8 by 15 feet patch of dirt, which is by itself not a big deal, except that used to be where I had 50 feet tall pine trees. The stump was ground, but the root went pretty deep, so I had to level the part where there were still roots from that pine tree. Danny, you can come over and help me with digging up those roots from a 50-foot tall pine tree. And trust me, it's not budging, it's not going anywhere. Yeah, I'm not gonna dig it out. I'm probably gonna fill the rest of that patch, with more dirt until everything is level. It's actually easier that way, moving dirt, around the yard than digging up that root. Yeah, I was looking at my heart rate. My normal heart rate is around, when I'm, just kind of standing and doing stuff, is about 75 to 80, and it's still 105, 106 right now. In other words, I have not recovered my heart rate, going back to the normal range, which means the body is thinking, what were you thinking? Overexerting yourself like that. All right, so we got about 30 seconds to go. And the first thing I'll talk about is just the release of the relations assignment. It's just homework. You have a week to do it, so there's plenty of time. You guys can ask questions on Monday or anytime before the assignment is due. You can use the questions channel, but I would say just be careful how you ask the questions. Instead of giving you the answer to these questions, you might want to present the questions as a concept question and use hypothetical examples to ask those questions. Just the fact of coming up with examples is already going to help when it comes down to understanding the concepts. All right, so it is time. It's noontime, and I'm going to get started here. This is your latest homework assignment that is assigned to you. It is due on March 9th, which is 1 week from today at noontime. So you get about exactly 7 days to do it. So with that out of the way, we're going to continue to talk about propositional logic. So last time, we were concluding with the rationale of why this topic is important, other than, well, it's in the curriculum, so I better teach that stuff. So that's not really a good reason to teach a specific topic. I really want to relate it to things that people are doing, okay? Why it is actually applicable. So for that, I am going to do a little Google search, and we'll look for heart. Let's see. I think that's it. Heart bleed is a bug that led to vulnerability. This is open source too, so open source code is not immune to having bugs that can potentially cause security issues. So I will leave it up to you guys to look it up and read it for yourself. But basically, this is a software bug um, that led to an exposure of secure keys in the SSL TSL level of encryption. So the question is, how does this relate to what we are talking about? Well, this happens because somebody wrote some code that was incorrect. In other words, it did not account for certain cases, and in those special cases, the program misbehaved, and as a result of the misbehaving, it's allowing certain things to leak through, including the encryption key, which is really important. All right, so why is it important? But how does it relate to what we are now talking about, which is propositional logic? So as it turns out, there's an entire branch of computer science, called automated verification. So that entire branch, is dedicated to the research of automated theorem proving, so that you can give that program another program, in C or whatever programming language. C is actually a very awful programming language for automated theorem proving. But, so you basically specify an algorithm in some programming language, and you specify the initial condition. In other words, how can we describe the input to this program, and then you specify the expected output of the program as a condition. Now you probably still remember, we actually spent a little bit of time to specify what would be the correct description of the result of a sorting algorithm, and that it seemed it should be pretty easy, right? But we actually spent quite a bit of time to describe what is the proper output of a sorting algorithm. So now, what we want is to have a program to automatically go from the initial state of your sorting program, what you can assume about the input, and it will go through the program statement by statement, expression by expression, and it will prove at the very end whether the expected outcome condition is met or not. So we want that to happen, because if we could do that, then this is not going to happen, because there will not be programs where we have already tested it with certain test cases, but we did not think about testing these programs from a hacking perspective, and as a result those some of those bugs went unnoticed, and then it became a problem later on. So I'm hoping this is helping you guys to understand the relevance of what we are talking about here versus what people are actually trying to do today. Now this is really interesting in a certain historical perspective, which is unique to me because you guys are younger and you won't have the background to understand historically why this is kind of interesting. Automated theorem proving is nothing new. Okay, it is nothing new. Back in the 80s, okay, I would say mid to late 80s, there was a lot of effort in order to try to get computers to prove theorems. In fact, certain programming languages were invented just for that purpose. Prolog being one of those. And unfortunately, at that time, computational power was very, very limited, because the internet was at best at its infancy. So we don't have a whole lot of networking. There's not a whole lot of computational resources. Mass store was super expensive at the time, so we simply did not have the hardware to do much about it. There's all kinds of theory, of how to do it, but practically speaking, there's not enough processing power to do anything. Now we have all the well, not I shouldn't say all, but now we have plenty of processing power, and so this topic was revived, okay, revived, because the importance of automated theorem proving is actually more important now than back in those days. Back in those days, how can you get a computer infected? You can try to infect a computer using a 1200 BPS modem. It's going to take a while to spread that virus, right? The most common way to spread a virus was floppy disks. Okay, there's a floppy disk. You put Microsoft Word document with some visual basic script that infects a computer, and then you have to take that disk from one computer to another computer physically to infect all the computers. Um, yes, SneakerNet, exactly. So the speed by which a virus can spread, or the importance of cybersecurity, is not quite as bad as what it is today. And as a result, even though automated theorem proving was an interesting topic, from the academic perspective, it wasn't really that important to industry. Nobody cared. Okay, now, well, guess what? People do care, because if your operating system, or a very crucial part of your operating system, has a security hole, that can be really bad, right? Because everything is getting automated. So there you go. Oh yeah, I just got rid of a whole stack of floppy disks myself, sitting on the shelf. Um, they're obviously not useful anymore because each one can only hold 1.44 megabytes of content, and that's before formatting. After you format, you don't even get that. All right, so getting back to the low-level detail stuff here. So I went back to this topic and go like, is there a better way to describe this thing? Yes, I have zip drives as well and jazz drives as well, and those are pretty much obsolete as well. 100 megabytes per disk is not a whole lot these days. They are now making SD cards that are capable of 1 terabyte already, and you can literally say that my dog ate my homework now, because having a dog to swallow an SD card, the micro SD card, that's not unconceivable. I mean, if you're just gonna wrap that thing in bacon, I can bet you that a dog will take it, it will just eat it in, I don't know, 2 seconds, one maybe even less. So there we go. All right, so getting back to here. All right, so this is where we left off. Okay, where we left off is, what about zeta? Okay, what about the elements in zeta? What does it mean? What does this set mean? What is each element doing in zeta? So we are going to try to answer this question today. This is just added a little bit before class because I was thinking about this and go like, well, maybe I can explain this a little bit better using this particular way. Now, sometimes when I think there may be a better way, it may not actually be a better way. Okay, maybe it's more confusing, but we'll go ahead and give it a try and see whether that works or not. That's what we use Pentium processors for, because those are notorious for the thermal output relative to the processing power that it has. So it generates a lot of heat, but it doesn't really do a whole lot of processing. Anyway, so what we're going to do here is, uh, okay, so if you guys want to see, how much heat a processor can give out, I'll give you guys a link later on. Okay, it's a very slight explosion of a processor, and it blew a hole on the table. I think some of you might have seen it already. Yeah, but we'll do that later. All right, so what we're gonna do now is, so now we need a lot of focus because there's a lot of symbols that we're gonna use here. So focus, focus. So when I need people to pay attention, the mental image that I got is, Sifu in Kung Fu Panda telling Po, focus, Po, focus. That's exactly what we need to do now. All right. All right, so we are defining a set called W, and we have seen this from the lecture on Monday. Okay, it's beta such that is a well-formed formula beta. In other words, we are simply saying, okay, W is a set of all the well-formed formulae based on whatever alpha and omega that we are using in the propositional system. So assuming we know what alpha is, what omega is, now we can kind of say that even though it would be kind of pointless to enumerate all the elements of this set. We kind of know what this set is. Okay, it has all the syntactically correct expressions given what symbols we have and also what kind of operators we have. So are we okay so far? Does everybody understand what W is representing? This is actually going back to the content of Monday, because this notation was used exactly, the same notation was used on Monday. Are we good so far? All right, cool. All right. So, in other words, W is the set of all well-formed formulae or formulas with respect to the alpha and omega in consideration. Iota is a subset of W because I is the set of all well-formed formulae that are given to be true. In other words, the expressions in I are well-formed to begin with, but on top of that, they also have special meaning because these are given to be true to begin with. So do we have any questions about why iota is a subset of W? I'm just focusing on this one statement here. No questions? Exactly, because well, not so much because they are axiomatic, but because iota contains well-formed formulae that are known to be true. At this point, I just want to know, are they well-formed? Well, guess what? I just said, right? Everything in iota are well-formed and given to be true to begin with. So I don't really care whether they're given to be true or not, but they are definitely well-formed. Is that part okay? Exactly. But we are not so much, we're not concerned about whether they're axiomatic or not. We are concerned about whether they're syntactically correct or not when we look at this particular subset relation. So we're good? All right. So now we're going to define another set, which is D, and D is a subset of W, so that D is a set of well-formed formulae that are derivable from well-formed formulae in I. Okay, so this requires a little bit of explanation, but I want to tell you what D is about first, and then we'll start to talk about what elements D is going to contain. So D is going to be a subset of W because everything in D has to be a well-formed formulae, but on top of that, we also want those to be derivable from elements of I. So this automatically means I is a subset of D because you can kind of imagine that we have a null transformation where it doesn't actually transform anything. Okay, whatever is the input becomes the output. So that would basically make everything in I to be automatically in D, and as a result, I is a subset of D. Are we okay with this? Lost on D and I. All right, so D is derivable. Okay, D is the set of all the well-formed formulae that are derivable from well-formed formulae in I. Is that okay? I'll talk about what derivable means later on. But at this point, we're just going to say they are derivable. So the main point here is: do you think an element of I is derivable from itself? Can I make a stupid transformation where whatever is the input becomes the output, and then I can just claim, okay, so everything is I is automatically in D because all the elements of I can derive to itself? Yeah, we'll do an example later. Okay, all right. So we'll talk about what is a derivable in the next paragraph. Okay, but at this point, the most important part is, every element in D is somehow derivable from the elements of iota. All right. So I think once we get an example, it'll be more clear. But I cannot explain the example until I have kind of explained what the elements of zeta is going to do. All right, so let's see if we can kind of push this. Okay, so we're going to assume that theta, phi, and psi are elements of alpha, because that's actually how we define the alpha in the example. Okay, so in this case, I'm just going to make the assumption all the Greek letters. Okay, that's basically all the Greek letters in alpha. They're called schemata. Each one is called a schemata. Each element E of zeta, so now we are talking about elements of zeta itself, has the following format. So this is the format. So the format has 3 parts per se. The first part is M. M is a set. We'll talk about what elements are in M later on. This symbol here is called infers. It's basically just a separator separating the left hand side from the right hand side. And then on the right hand side, I'm using this notation of WFFQ. Q is just here to say a specific well-formed formula. And in the well-formed formula, on top of operators from omega, it's going to make use of theta, phi, and psi. So I know this is really abstract at this point. So what you want to think at this point is M is a set. Now, what elements are in this set? We'll talk about that later. This is a symbol separating the left-hand side from the right-hand side. So by itself, it doesn't really have a whole lot of meaning. And then WFFQ, theta, phi, and psi is basically just a well-formed formula that makes use of the Greek letters theta, phi, and psi. So they're abstract at this point because I'm trying to make this as general as possible. So we're still doing okay so far. M is a set. This is some kind of well-formed formula involving the Greek letters theta, phi, and psi. It's just a representation thing at this point. There is an example right at the end of the paragraph that we are on. So, all right, so let's see what Danny has to say. It's kind of hard to tell if I'm getting it right without an example. So when we get to the example, it'll be pretty clear, okay? For example, an element of omega may look like this. So the first thing we notice is there is this symbol here. It's called infer. If you want to type this in LaTeX, it is called V dash. Okay, backslash V dash is going to give you this symbol. So the symbol is really just separating the left-hand side from the right-hand side. The left-hand side, which is the set of M, remember this is just a format. Okay, this is just really describing the general format of an element of zeta. In this case, this is a very specific example of an element in zeta. So in this case, we have a set because we see the braces enclosing the elements, and then inside we can see, this is a well-formed formula. Right? We have theta implies phi, and then the second one is also a well-formed formula because we have phi implies psi. Now, obviously, this is implying that we have implication in omega, but we already, when in the example that we have been talking about, implication is a part of omega. And then Luke is asking, should it say an element of Z may look like an element of... Oh, you're correct. It is Z, not omega. Luke is correct. Let me fix that. I just typed it this morning, so didn't really have a whole lot of time to proofread it. So let me fix that first, and then we'll go from there. Thank you, Luke. Alright, so let's see. Okay, so that's why Danny was confused. Yeah, I would be confused too if I was reading this. Alright, there we go. And then refresh, and then I have to scroll back now again. Alright, so it is fixed now. That what used to be omega is now zeta. For example, an element of zeta may look like this. Okay, so now it's good because this is what a transformation rule may look like. So we have theta implies phi as one element. It is a well-formed formula by itself. Okay, that's why that's what elements of M should look like. Each one should be a well-formed formula involving the use of the Greek letters. And then the second one is phi implies psi. So are we good so far in terms of the left hand side of the infer symbol? It is a set of well-formed formulae, and sometimes you can have zero. Okay, so later on I'll give you some examples of what do you mean by it can be zero. What do you mean by it can be empty? But right now it is not empty. So right now we have two well-formed formulae involving the Greek letters. So in what way are these transformation rules? Okay, so the left-hand side, or M, specifies constraints. Basically, it's specifying constraints so that you can search within D, okay, within the set D, you can search for expressions. You can search for well-formed formulae that would match these particular patterns. And once you have a match, okay, then you can fire, quote unquote, fire the rule. And when you fire the rule, it will put this extra thing into the set of D as well. It's basically saying, how do we define the membership of D, the set of all the derivable well-formed formulae based on what is in iota to begin with. So this is the condition in order to fire the rule. This is the output of the rule, so to speak. Is that answering Elijah's question? All right, cool. Now, I do have to emphasize that theta can match anything within the set of D. Phi can match anything within the set of D. However, this phi here has to be the same as this phi over here. So now we have a constraint of the right-hand side of one implication has to be the left-hand side of another implication. Now this psi here can be anything within D as well. So that means theta and psi can potentially be the same thing. They don't have to be, but whatever phi is has to be the right hand side of one implication has to match the left hand side of the other implication. So we are looking for patterns using this particular set here. Once everything matches, once we have a match for all of these rules within this set, then we basically say, okay, take whatever whatever this theta is representing, take whatever this psi is representing, and now we have a new well-formed formula that is also considered derivable from iota. All right, so let me check the text messages. Is Z something that is given to us for a specific calculus? That is correct. So depending on the purpose and who is doing the processing, let me see if I have that link here, because I might not have saved the link in Canvas. But basically, there are other professors, teaching the same class, and they have already come up with a set of these rules. And let me see what Boolean algebra is about. There we go. Okay, so basically we want the transformation rule. We want to capture all of these as a part of the transformation rules. You're basically coding an algebraic system as grammatical rules so that you can do all the derivation mechanically. So we can derive the right-hand side given the constraints in M. Yes, so M is basically specifying some constraints for pattern matching. Once you match all the patterns in M, then we specify whatever is on the right-hand side to be derivable from the pattern on the left-hand side. All right, so the elements of M are from set D. M. Yes. So the elements of M have to be elements of D to begin with in order for the rule to fire. It's okay. I take it back. Okay, I take it back because what you have in D are specific well-formed formulae, but they are not the ones using Greek letters. They are the ones using P, Q, R, S, T. The Greek letters are, in a way, they are basically wildcards. Okay, it's just like when you specify a file name in DOS. Okay, in Windows, you can use the asterisk symbol to match anything, right? And then you can say star dot star means the file name can be anything, and then the file extension can be anything. Or you can specify star dot doc, DOC, then you're specifying, okay, the file name can be anything, but the file extension has to be doc doc. That's kind of what theta, phi, and psi are doing. They're wildcards. But they are not just asterisk because we need to be able to refer to these on the right hand side. So you can kind of look at these as named wildcards so that we can refer to the name of each wildcard so that we can specify what is the new derivable formula. It's a little hard to describe this. If you guys know how to do regular expression and use groups within regular expression, so then it becomes easy to explain because that's basically what these things are. It's kind of like substitution. Okay, I'm not sure how many of you know regular expression and substitution, but it's kind of like that. This is specifying the patterns that we are looking for, and we are specifying certain types of wildcards, except they are named, so we can refer to that placeholder for something called theta, that placeholder called phi, that placeholder called psi. Okay, so all of these are names of placeholders. And what are they holding? What are they placeholders for? They're placeholders for well-formed formulae. So each one can match basically an entire well-formed formula that can be like gigantic and complex. Okay, it doesn't matter because the restriction is, even though theta, phi, and psi can all be super duper complex, the restriction here is we are looking for two implications within the set of D, and we are also putting the extra restriction that the right hand side of one implication has to be exactly the same as the left hand side of the other implication. Now, if you can find a pattern like that, then we say that the left hand side or the constraints have been met. Once the constraints are met, then you can now claim that whatever we use to substitute theta over here will now be the left hand side of a well-formed formula. Whatever is psi over here, which was only implied by phi, as a pattern match, but now we can make I shouldn't say make a new, but now we have a well-formed formula that skips phi and it goes straight from theta implies psi. And now we can claim this one is also derivable from iota. Alright, so I'm reading the text now because as I was explaining, I was spending all my brain juice on just all the concepts in my head, and then try to in programming term, stringify. For those of you who know what is JSON stringify, that's what my brain was trying to do, is to stringify all the concepts that are kind of like in different order, and it's structured but it's not sequential, and trying to make all of those things presented in a sequential way is difficult. Okay, so let me go back and read the text channel right now. Okay, so there were some jokes about doing some dangerous delete operations, and I think, Chris, you need to use uppercase R, not lowercase r. So let me do that correction first. There we go. Because uppercase R means recursive. I don't think lowercase r means the same thing. And then Danny has a serious question. So using Z, we can derive. It's not about deriving. It is classifying which one is derivable from iota. So let me say that one more time, okay? Using Z and starting with I, D is basically things that are derivable from elements of iota. And deriving would make use of elements of zeta. So we basically, okay, I'm reading Elijah's feedback here. So we basically say we can infer the right-hand side from the left-hand side. Yes, yes, that is what it is. But, it is important to understand that this is actually just pattern matching. The left-hand side specifies what pattern we are looking for. And then the right-hand side says, okay, once you have matched all of those constraints, on the left-hand side, then you can claim whatever is on the right-hand side to be derivable. But every single time we fire the rule, these Greek symbols would be instantiated to specific things in specific well-formed formulae. All right. All right. Cool. And I might have made a mistake down here too. Let me see if I have made that. See if I made a mistake. So right now I'm not going to say what I am thinking about, but if I do make that mistake, I will tell you guys what it is. All right. So now we have the vocabulary to describe membership of D. So all of this stuff here is just to build up the vocabulary to describe membership of D. Now the first one is easy, okay? I as a subset of D, everything is I is in D. Yeah, we got that, okay? Because we can just derive, we can make a very simple non-transformative rule in zeta. I'll just describe it in my notes here. Let me, okay, give me a second here. I just want to make sure that I do not have a old note, still open. Okay, there we go. So today is 2022-0302, and this is marked down. There we go. And now we can turn off dark mode. All right. So what was I talking about? Right, a null transformation. Okay, one that doesn't really do anything. So I can show it like this. Actually, I'm not really sure that's going to be helpful, but we can always do something like this. It's not going to do any harm for sure. There we go. All right. So this transformation rule basically say, hey, give me something, and I'll give you that thing back. That's useless, right? Because it's not going to make any more things derivable. So in order to make this usable, in the sense that we can have some starting point, we can just change this a little bit. Okay, just a tiny little bit. We'll just say that as long as we can find this in iota, it is now derivable. We'll make theta derivable. Is that making any sense? I just need this in order to make everything in iota to be a subset of what we are now constructing as the set D. Is that part okay? I'll just kind of pause a little bit and stop talking. All right. All right, so let me go to the text channel and answer the questions sequentially. The first one is this for set D or Z? So this is a rule in Z in order to seed the set D so that we have something to start with. So we have some initial membership in D to begin with. So that's 1. So if you want to, so I can do something like this. So basically, this entire thing is a rule, and as long as this is in zeta, then we are all good. Then we can seed the set D with everything in I. All right, next question. Explain it once more, please. Not sure what it is referring to. If it's everything that I just talked about, I'm sorry, I cannot do that. It is not because I refuse to do it, because it's because I really cannot remember how I said it to begin with. So the next question is, so D uses Z to get its element. Yes. So we can basically, with this one simple rule, we can seed, what initial elements we can start with in D. Because otherwise, D is an empty set. We cannot describe it recursively referring to itself without a base case. So this is basically providing the base cases so that we can say, okay, so how do we get started with populating elements in D? This is how we can get started. Easy peasy, right? Just take everything in I and just say, okay, if you're in I, you're now in D. So at this point, D is nope. Okay, all right. So I think it is important to differentiate what D has. Okay, so let us use an example. Okay, so for example, all right. So the example is going to have define alpha first, right? So alpha is going to be the same as what we had before. So we're going to define alpha as 0, 1. Those are the constants. And then we have P, Q, R, S, T. And then we'll have the 3 Greek symbols that we have been using all along, which is theta, phi, and psi. All right, so this is how we define, alpha. And let me get to the text channel just to be sure everything. Luke just deleted his text, but the LaTeX version is still here. Everything prior to the element of Z is an element of Z. Okay, so yes, let me add extra parentheses to indicate what is the element. Okay, the element is going from here all the way up to here. That is a transformation rule. This entire thing is a transformation rule, and zeta is basically a set of transformation rules. So we are going to stick this one in to zeta just so that we can have a connection between D and iota. So we can seed the set D with everything in iota. So just hold on a second. Let me finish the example, which is basically a repetition of what we used on Monday. All right, so we're going to define omega 1. Omega 1 are the operators that only require one single operand. So in this case, in most logic system, we will only have logical not, as an operator that requires one single operand. And then we have omega 2. So omega 2 is the set of all the operators that require 2 operands. So typically, if you are working with a system that eventually is going to be a person using it, or is trying to replicate how people do things, then you have conjunction, which is a wedge. You have or, which is the V. Then you have right arrow, which is the implication. Then you have the left right arrow, which is the if and only if or equivalence. Let's see, am I missing anything? I think those are it. Okay. So omega 2, okay, typo. Omega 2, there we go. All right, so we have, and then omega itself is really just the union of all the omegas. So omega is defined to be omega 1, and then we have a union, which is a cup, omega 2. So are we good so far? I mean, this is really just a repetition of what we did on Monday. But I do want to confirm that we're doing okay at this point. Okay, all right. So so now we can kind of take a look at what is in W, right? So we saw all kinds of crazy stuff that can be in W, but this time I'm gonna give you something else that can be in W. So W doesn't care about whether something is true or not, right? So this is in W by definition, because W is the set of all well-formed formulae, and because 0 is a constant, it is in alpha. Everything in alpha, okay, each element of alpha is automatically a well-formed formula, and as a result, 0 is in W. Are we good so far? Connecting what we are talking about today, which is the set W, with whatever we talked about already on Monday. So are we doing okay so far? And you don't have a problem with 0 by itself is a well-formed formula. All right, cool. All right, cool. So now we can say, okay, so if 0 is well-formed, then we can use it to make new things that are also well-formed, right? So now we can say, hey, this is also well-formed, right? Because 0 by itself is well-formed, and in order for a well-formed formula to use a conjunction, we just have to make sure that each side of the conjunction is well-formed to begin with. This meets that requirement. And then from here, we can derive something even it's bigger, but it's also just as silly, because now we can just say, okay, now that we know 0 and 0 is well-formed, then so is 0 and 0 on one side, 0 and 0 on the other side of another conjunction, right? Now, is this meaningful? No, this is definitely not meaningful in any way, because this is all just saying, okay, you can just say 0 instead of 0 and 0, and then the whole thing and 0 and 0. That doesn't really get us anything. But I'm just illustrating what elements are in W. So eventually we'll get to elements in iota. So now we say, okay, what about in iota? Now this you have to be careful, because whatever is in iota has to reflect, quote unquote, the reality where this logic system is being applied to. So if you want to model the reality of text classes being super boring, people are falling asleep, but the silver lining is if people fall asleep in my classes, they feel refreshed after the class. Okay, if that is the reality that you want to reflect using a logic system, then you kind of have to be careful what you put into iota. So what usually goes into iota would be 1. Okay, 1 is the constant that we use to represent true, so it kind of makes sense to put 1 in iota. The negation of 0, okay, so that's kind of how we define false, right? False is not true, so it kind of makes sense to put not false into as a well-formed formula into a set of known to be true expressions. Okay, so that kind of makes sense, not a problem. And then we have so quoting from the example on Monday, so we have P implies Q, and then we have Q implies R, and I think that was it. Okay, that was the entire iota that we used on Monday. All right, so now I'm switching back to Discord and read the messages over there. So the cardinality of W is infinite. Yes, most of the time it is. It really depends on what you put in omega, and as long as omega is non-empty, you probably end up with a W that has an infinite number of elements. So for the most part, yes, generally speaking, yes, but you can have a deformed system that is totally useless where W is not infinite. Next question. I thought refresh was by learning, not sleeping, and that is one way to look at things. Well, it depends on how you what classify as refresh. Okay. Next one. Refresh memory is learning. Refresh energy is sleeping. Very good, Nathan. That is Very good. It's a good clarification of what kind of refresh we are talking about. But, okay, so this is the system that we have right now, okay? So IOTA has just a few things, okay? Yeah, thumbs up is right. All right, so now we want to say, what do we do about zeta, okay? So we are going to construct zeta, just kind of gradually, okay? So the first thing we do is we specify the cloning rule, okay? Let's clone everything in iota into D, okay? So that's the first rule that we're going to put into zeta. So instead of using z equals to and then the brace and stuff like that, my watch just buzzed me, but I'm not going to take row today because it would be it's going to be bad to break away from this because now you already have a lot of context in your head, and I don't want to lose that. Okay, so I'm not going to take row today. All right, so now we're going to put the first rule into zeta. So that's just whatever we had earlier. Okay, we have theta in I, and then v dash zeta. Oh, I need to. Okay, I need an extra close parenthesis over here. All right, so this is the first rule. Oh, I'm missing a open brace, which is here. There we go. All right, so this is the first thing I specify and go like, okay, so what qualifies to be? Oh, there's one more thing. I forgot about the v dash. Also needs. Okay, the close parenthesis is not supposed to be here, and then we have theta here, and then close parenthesis go over there. There we go. Okay. And then I delete in. There we go. All right. I don't think they would refer to without. Oh, okay. So that's a. Oh, okay. Oh, that's an off-topic thing. Okay, so I'm gonna turn off. Okay, I hope you guys know how to turn off notification from a channel. You go to the channel, you right-click, and then you go to mute channel, and you can specify a time. So if you just say I don't want to be distracted in class, but later on I want to be entertained by everything in off-topic, you can just turn it off for an hour or 3 hours or whatever amount of time. But if you want to turn it off permanently, that's fine too. So that's an individual setting. You can just basically ignore certain channels so they don't ding you all the time. All right, so this is going to be the first rule. So just having this rule means I can now already specify certain memberships in D. So just having this rule, I can now say everything in iota is also going to be in D. So at this point, I can say 1 is in D, and not false is in D, and then we have P implies Q is in D, and then we have Q implies R is in D. So are we good so far? Just because of this one single rule in zeta, we can now establish the seed in D. I call these seed because we can now start to say, okay, but what can we do about these things? Can we derive something else? But we have to start with something. Okay, in order to derive something, we have to derive that something from something else. Most of the time, not all the time, but most of the time we want to derive something from something else. So are we good so far in terms of relating a single transformation rule of zeta in order to determine what is now a member in D, which is the set of all the quote-unquote expressions that are derivable from iota. All right, cool. So this is all good. So true is in there when false is not. Well, false cannot be in there because iota are the expressions that are known to be true. False is the opposite of that. That's why we have not false in D. Exactly. So Danny is correct. We are defining false as we're defining true as not false. Okay, that's the right way to put it. Okay, so now here comes the important part, because this specific rule here is not really that useful. Okay, all it does is to say, okay, this is how we can seed the set D with stuff that is in iota. So we don't have to say, yeah, we don't have to make a special provision, just to say, okay, this is a special case. Everything in I is automatically in D, and that's not because of a transformation rule. So we are just make generalizing and say, yes, the transformation rule is responsible to put everything into D to begin with. So it's more or less just kind of making things a little bit more consistent, but it's not really super duper useful. But this one is going to be useful. So now we can say, once again, the left-hand side of a transformation is a set. Okay, it is not a single pattern; it is a set of patterns. So in this case, I'm specifying the pattern as theta. Okay, this is actually in the notes, so you don't have to copy it down. I'm just gonna repeat it here. So theta implies phi is one element, and then phi implies psi is the other element. So this is a set, and if I can find things, okay, to match theta, phi, and psi, then we can infer, okay, which is v dash, and this time, I use a new well-formed formula that only makes use of theta implies psi. So phi is completely missing from this entire thing. Okay, so this is a rule, and let me specify this is now an element. This entire rule is now an element of zeta. So I'm basically just showing you what is in zeta element by element at this point. So this entire thing is in zeta. All right. So are we okay so far? Does everybody understand what this means? In other words, I'm only specifying, oh, by the way, there's another element in zeta. This is the other element. This is the other transformation rule that we're going to put into zeta. Are we good with that? All right, cool. So now what we're trying to do is to say, can we find something in D existing, in D, that looks like this, okay? That looks like, something blah blah implies blah blah, okay? You go like, yeah, we can find two of them. In fact, we can find this is, something implies something, and so is this, okay? But we have to be careful which one is matching this element and which one is matching the second element, because in order to match both elements, one is going to use a specific expression as the right hand side, and then the other one would use the same expression as its left hand side. So now we have this extra constraint here and say, oh, so we cannot just kind of randomly match the implications into here. This P implies Q is only going to match this specific rule here, because we need Q to be the left hand side of the other expression. So Q implies R is going to match phi implies psi. Are we doing okay at this point? Because this is the most important part. I mean, this is really the most important part to understand what a transformation rule is. It is basically going through everything that is in D at this point, and then you say, can we do some pattern matching here and make all the constraints of the left hand side of the transformation rule satisfied? That's basically what we are trying to do. So I'm going to write it down here as well. Okay, so I'm going to write down and say, by making theta the same as P, making phi the same as Q, and making psi as R, we can now fire the rule. Okay, is that okay? Does everybody understand, how we are binding letters from the English alphabet PQR into the schemata, which are represented by the Greek letters, theta, phi, and psi, in order to say, yep, we can do this pattern match. We find something that can make this work. All right, so I'm reading the text channel. So did you derive it from iota or make it up? If that it is referring to the rule of zeta, I am creating these rules because each one is corresponding to a rule in Boolean algebra. Zeta is given to us, so he make it up. So I'm making it up, to be consistent with Boolean algebra, so that when this is all done, I have just specified a syntactic, mechanical, grammatic system that would also be matching how we humans do Boolean algebra. Because the idea is to capture um, the Boolean algebra rules in a way that is syntactic and mechanical. So this way we can tell a computer and say, hey, these are the rules. You just match, fire the rule, derive something, match, fire the rule, derive something, and then eventually we wanted to derive something that is quote unquote the target. We will specify a complex, usually not in this case, but usually we want to specify a really complex, well-formed formula and say, can this really complex thing is it derivable from everything that is known to be true to begin with? In other words, this is how you prove a theorem, right? Because you're given all the axioms, you're given all the assumptions, and your teacher, your professor in math is saying, okay, so I want you to go step by step and show that this expression here, this statement here, is also going to be true. We are trying to get the computer to do the same thing here. All right, so I'm getting back to the text channel. So you derive the transformation rule from Boolean algebra. Yes. Now, it doesn't have to be the case, okay? You can make any rule you want, because it doesn't really... These symbols here, when it is inside in a system like this, in propositional logic, these things are nothing more than just symbols, okay? They have no meanings. The meaning of these symbols are coming from the transformation rules, because the transformation rules will basically specify what operator are we using here, and what operator are we using here, and what operator are we using here. So it is a combination of the rules to basically give quote unquote meanings to the symbols in omega. So you can make any rule you want. It's just that if you can end up with a system that has no actual practical use, because it doesn't really match anything that we want to do with any type of algebra system. So we are describing a mechanism that can be used to prove theorems automatically if we specify the right rules. At the same time, the mechanism is blind, okay? It doesn't care about the meanings of conjunction, disjunction, and whatnot. So if you specify some, rules that does not necessarily match, Boolean algebra, it will still quote unquote work, but it doesn't match anything. I mean, the result is not going to be useful in that case. All right, so I'm reading on the text channel. Have you given the entire set of zeta just a few elements, because I want to illustrate how the elements fire first. Okay, so I'm not even done with that example yet at this point. Right. Okay, so Danny is correct. I have only given you 2 elements so far. Okay, in order to illustrate the concept of how we apply each rule in zeta. And then Luke said, so we are sort of connecting arbitrary axiom and with generally accepted axiom Boolean algebra. That is correct. Okay, so what is in zeta is the logic system itself. What is in iota is what is specific to a certain reality that you want to reason with, okay, or reason within. So So one has to do with iota has to do with reality, and zeta has to do with the actual nature of logic. So someone, okay, someone with too much time on their hand can watch Harry Potter, okay, and and come up with an iota to model, that universe in Harry Potter. But it will still be using a normal logic system to reason things out, right? So now you can put in all of those, you can put in all the observations and all the rules in the world of Harry Potter, and then come up with a theorem or come up with an expression, you know, and you want to know whether that's going to be true or not based on the model that you have created for Harry Potter. But to prove whether the statement is true or not, you're going to use regular logic, okay? Because we are assuming we are going to use the same kind of logic, even though the reality is different between realms of based on movies and books. So you're going to use the same zeta, but you're going to use a different iota depending on what reality you're trying to model after. I'm not sure whether that's going to help or not, in terms of explaining what iota is representing versus what zeta is representing. There's no egg or chicken. They're both components of something. One does not make the other. They serve entirely different purposes. I think that's going to be the only thing people remember out of this lecture is there was something about Harry Potter that relates to propositional logic, and that was it. All right, so Danny said, like, you could create a system where 0 is true, 1 is false, and elements of zeta are not derived from Boolean algebra. But that would not be very useful, right? Because now you have a system that does all the same pattern matching. It can say what is derivable from iota, but it's no longer reflecting the kind of reasoning that we want the computer to do when we wanted to prove theorems. So the idea is, yes, you can make any rule you want. Okay, you can make alpha whatever you want. You can make the omegas anything you want, and most importantly, you can make zeta anything you want. Okay, you can come up with your own rules. The question is, what is considered derivable? Is it meaningful anymore? That is the question. Can we define shortcut operations in zeta like that? Okay, yes. So let me finish this one first, and then we'll get back to Nathan's example. All right, so we'll go ahead and say, and as a result, okay, I should probably give these things names now, but I'm just going to say that this particular rule can fire. Okay, so as a result, the rule fires, and P implies R is in D. There we go. So I'm going to put extra parentheses just to emphasize that we are saying that the expression, the well-formed formula, P implies R is now in D. It is now considered derivable because P implies Q can be found. Q implies R can also be found as things that are in D to begin with. And according to this rule in zeta, once we have met the criteria or match the pattern matching on the left hand side, then we fire the rule, and whatever is specified on the right hand side is now considered derivable. Alright, so let me get back to the text channel. And then Luke said this class feels like it's dipping into epistemology. I do not know that term, But good thing I can just double click on something, right click, and say Google it. Or not. Oh yeah, you can do it. Search with Google. So that term epistemology is a term in philosophy, the theory of knowledge, especially with regard to its method, validity, and scope. Yep. My son is in high school and he actually has classes, of theory of knowledge. I have never taken that. Chris is saying he is not dipping. But if you think about it, it really does make sense, right? Because this is how I look at things. I drill all the way down until I hit the hard pan, and I cannot drill anymore. There's a point where I cannot drill anymore. Okay, trust me, there is a point. But I would try to kind of get things as break things up into the most elemental form first, and then I'll go back up and synthesize things out of those more elemental concepts. That's just the way I learn things. That's just the way I think and I process, things around me. Um, I was told that most people do not do it that way. So I can say that has been expressed to me by multiple people in many of my circles. All right. I learn by okay, so I do not learn by examples, but I would use examples to validate my understanding. In other words, I would formulate all of these theories in my head first. Okay, so everything is abstract and they're just kind of floating in space, in the void. But then I'll come up with examples and go like, okay, if my understanding is correct, this is going to be blah 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 blah. Okay, and then I'll test out those theories by. So I would use examples to confirm my examples, my understanding. Sorry, to confirm my understanding. So I'm not really sure whether that classifies as learning by examples or not. All right. So are we good so far? I mean, are we understanding, how transformation rules in Zeta make use of items or elements in iota, and it would just get more and more things into D, which is the set of well-formed formulae that are derivable from what is known to be true to begin with. So are we getting a better understanding of all that stuff? All right, Luke said yes. Okay, excellent. All right, so let's go back to the example that Nathan mentioned. Okay, so Nathan mentioned a rule. So we are basically specifying more and more rules that are usually in propositional calculus. So the rule that Nathan has mentioned simply says, okay, if we have, generally what is, theta and phi, if we can find these two patterns, then we can infer v dash theta and phi. And that is a rule. And this is usually in zeta, if the zeta is intended to replicate how we do Boolean algebra. So that is what captures what Luke said earlier. All right, so you can see how this is going to be applicable right away, right? Because what do we have in D at this point? Even not counting this thing here, this is new. So even if we do not count P implies R is an element of D, we still have a bunch of stuff, okay, that we can use to fire this rule, because this one says, oh, just give me a well-formed formula, we'll call it theta, and give me a well-formed formula called phi. They can actually be the same thing. So if you find anything in D at this point, say 1, right? You can now say, oh, then 1 and 1 is also derivable, considered derivable, and therefore it is in D. So I'm going to write it out like this, okay? So I'll say let theta be 1 because 1 is in D to begin with, and then we'll also let let's see, what is the other one? Phi is 1 because that's okay too, because all we need are well-formed formulae that are in D to begin with. So now we can fire this rule, then we know the result, which is 1 and 1, and I'm going to put parentheses around it because I want to emphasize this entire well-formed formula is now in D. It is considered derivable now. And there's an extra dollar sign. Let me get rid of that. And I'll use an asterisk as a point. There we go. So are we getting a little better understanding now, of how the rules are applied? The left-hand side is a set that specifies, hey, we need to match these things, and then we're going to use whatever is matched to create something, possibly derive something on the right-hand side. Are we good? All right. Cool. All right. So let me look at the time. We still got 8 more minutes to go ish. So I'm going to give you guys something that is going to be like, what? How can this be an empty set? It's an empty set, and we can still derive stuff out of it. So now we can say, let's derive theta or not theta. And no, this is not Shakespearean. It's not English literature. This is as hardcore computer science as it gets. All right, so let's consider this rule in zeta. You look at this and go like, what are we talking about here? Well, theta just has to bind to a well-formed formula, okay? And it can be any, right? So this basically says if something, it only has to be well-formed. This has no restriction whatsoever that it has to be derivable to begin with. So theta doesn't even have to be derivable because there's an empty set here. If this is an empty set, if I specify theta here, then theta has to be derivable to begin with. But since theta is not even in the set on the left-hand side of the rule, theta can be any well-formed formula. Okay, it doesn't have to be derivable from iota itself. So now we look at this and go like, so how do we make use of this, right? So now we can say, since there's no restriction, the only restriction is theta has to bind to a well-formed formula. Okay, so I'm just going to specify a well-formed formula based on what is in alpha and what is in omega. Yes, that is what I said. I am not taking rho today because this is a very continuous topic. If I take rho, this is just going to break your concentration and the context that you have been maintaining up to this point. So now I can say let theta equal to, let's pick something that's not even that we haven't even seen before, okay? But I don't want to type too much stuff, so I'm just gonna make it easy. So P or Q, and then the whole thing implies T, okay? And you guys go, oh, okay, never mind. I forgot about the backslash. There we go. All right, so you guys look at this theta and go like, but this expression doesn't even appear in iota to begin with. Well, I don't care. The question is it well formed? Well, let's see, right? Or needs 2 things, and I am giving it 2 things to or. Okay, good. Implication requires 2 things. Okay, I'm giving it 2 things also. So this is syntactically correct, which means it is well formed. So now we can fire the rule. And now we can now say this thing is also in D, which means it's derivable. So I'm just going to do some copy and pasting here. Let's see what would be the easiest way to copy and paste. Yank to $. There we go. Okay, so one copy, and I'm gonna need another copy over here. Oh, okay. Okay. Now let's see what I'm gonna do. Alright, fine. I'm gonna do one more time. Yank to $, and then paste it here. There we go. Alright, so now I'm gonna use extra parentheses to emphasize what we are talking about. So the first part here is not negated, and then the second one is negated. So put extra parentheses around the entire thing. There we go. Alright, so let me go back to the text channel. So in this case, we aren't dealing with the truth, just well-formed. That is correct. And the reason why it doesn't have to be derivable is because theta is not in the it's not on the right, it's not on the left hand side, it's not in the set of the left hand side. So that means, theta is really just anything that is well formed. It doesn't have to be derivable itself. So I can choose theta to be whatever, okay, as long as it is well formed, it's going to be okay. And the reason why this is okay, this is actually making sense, right? Because you remember, these rules are completely syntactic. It is just mechanical, okay? It's just saying, okay, find something that is in W in this case. It's not in D, it's just in W. Find something in W, and now we can say that thing or the negation of that thing is derivable, okay? That's what we're trying to claim. And the reason why this works is because one of these two has to be true and the other one has to be false. So that means, it doesn't matter what theta binds to, as long as it is a well-formed formula which has a value of either true or false, then either it is true or the negation of that is true. And since we're putting an or here, that means, it makes sense, because if at least one side is true, the or is going to be true. So this is reflecting a certain rule in Boolean algebra, but the way we are presenting it here is syntactic. We are simply saying, okay, this is how we can make more derivable equations or derivable well-formed formula. So that's basically what it is. All right. So could we say P implies Q and Q implies R using the second to the last Z? Yes, that you can do. Yes. So using this specific rule, we can bind theta to P implies Q. We can bind phi to Q implies R. Then we end up with P implies Q and Q implies R. Yes, so that can be done as well. But it's not as cool as the first rule, because the first rule, this rule here, basically is quote unquote. Now, I hate to mix all the concepts, but sometimes it really helps, because this is kind of transitive, right? Because when you have P implies Q and Q implies R, then P implies R, that is what transitive is all about. Okay, so implication is transitive. If you look at implication itself as a relation, it is transitive. All right, so we are out of time, but I think this is good. Okay, so transitive property in algebra. I'm not sure whether there is such a thing called transitive property in algebra. In comparison, yes. So comparison are relations, but implication itself is an operator. It is not a relation. I suppose you can make it a relation by changing, implication into impliable. Okay, then it becomes a relation. So I should probably write it down here. Implies is an operator, but okay, impliable is a relation. I'm not even sure that's a word, impliable, but it sounds cool. All right. I was thinking package in transit. That's also relation. Equality is a relation, it's not an operator. An operator usually means the after the operation it give you a result which is true or false. Well, I suppose you can still look at it as an operator, but it's not a Boolean operator. And in this case, when we talk about propositional logic or propositional calculus, it is the logical operators that we are concerned about, not the comparison operators. But equivalence is like that too. Equivalence if A if and only if B, and B if and only if C does mean A if and only if C. So it also has that kind of transitive taste to it. So there you go. Yeah, similar idea, similar idea. There we go. Very similar. Okay, so I think we have accomplished quite a bit today because the understanding of what a rule is in Zeta and how it is applied. It usually is a problem in this class because in my current note before I modified today, it didn't quite explain that. But these examples hopefully will help you understand what a rule looks like, what are the components of a rule, and how we apply the rule to make more well-formed formulae derivable. Okay, so we are not concerned about true false anymore. I'm only asking, is it derivable? Because true false is a little bit harder to. It has a very inherent meaning, and derivable does not. Derivable simply means it's through syntactic manipulation. Can this be done? Okay, can we go from here, go through a bunch of transformation, just completely syntactic transformation, and end up here? That is basically what we're dealing with here. Is a mechanical system that performs syntactic manipulation, and we're just asking, is this thing here derivable from those things over there? If it is, and zeta is done correctly, then we have just proven a theorem. But that is conditional to using a correct zeta to begin with, because you can come up with a zeta that is okay, meaning that, yeah, we have all of these transformations, but are the transformations actually representing logic that we need to use to prove theorems? If it is not the case, then you have a fairly useless system because it doesn't represent anything that is actually going to be useful. All right, I'm just reading the text channel here. Please upload notes. Okay, I can certainly do that, but just be warned that when I take notes, and I explain things, everything makes sense, right? It is I think it's going to be a good idea for you guys to just kind of refer to my notes, but also come up with your own as you digest and go through my notes. So your job is to annotate my notes, and my note here is to annotate my module. So you're going to be doing annotation squared using your own words. But I think that is going to be crucial, if you want these things to sink in. Because at this point, you might say, "But I get it already. I'm getting this." Yeah, just ask yourself that question in 2 hours. You may not have the same answer anymore unless you annotate my notes using your own words. So I highly recommend people to do that, even if I release my note that I have captured here. In fact, I'm just kind of put this into the module itself because that kind of makes sense too. Yes, it's annotation squared because you're annotating annotation. So you're annotating annotation. There we go. All right, so I think we got enough abstraction for the week, right? It's Wednesday. So you guys have a nice weekend. I'll see you on Monday. Don't forget the homework assignment. Okay, that's for relations. It shouldn't be too bad, but some of the questions will kind of make you really think about what it means to be, let's say, anti-symmetric and so on. So that's kind of the whole point of the assignments. I mean, they're not supposed. It's not supposed to be easy. It's supposed to make you think, and kind of, it will help you understand what you may not be clearly understanding yet at this point. And the assignment can only be done once. Okay, once you submit, that's it. Okay, so do not submit until you're quite ready, that you're ready to submit it, because I don't want people to just kind of, okay, I'm just going to randomly try things out until I get the highest possible score. Trust me, there have been people who did that. Yeah. Alrighty. So I'm gonna kind of get out of this. If you guys have questions, go ahead and leave your questions in the text channel or in the questions channel to be even better. And then when I have time, I'll go there and answer all your questions.